Welcome to another engaging episode of ArXiv Preprint Server Daily AI Frontiers, focusing on the latest advancements in robotics. Today, the spotlight is on computer science robotics, a transformative field reshaping industries. This episode synthesizes 12 cutting-edge research papers, all published on April 24th, 2025. The objective is to uncover key themes, groundbreaking findings, and future directions in this dynamic area. Let's dive into the innovations driving robotics forward and explore why they matter. To set the stage, let's explore the field of computer science, robotics. This discipline merges computer science with the design of physical systems, encompassing algorithms for controlling movements and hardware for executing actions. Its applications span industrial assembly, surgical assistance, and even exploration in hazardous environments. The significance lies in its ability to enhance efficiency, safety, and quality of life. Today, the focus is on the most recent submissions to the ArXiv preprint server, showcasing the latest strides in this ever-evolving field. One prominent theme in current robotics research is advanced manipulation and grasping. This area focuses on enabling robots to handle objects with precision, often using dual arms for bimanual coordination, much like human capabilities. Studies, such as one by Yang and colleagues, develop techniques to predict gripper poses and object motion flows. Others, like Kay and team, explore learning grinding skills from human demonstrations. The impact is significant, paving the way for robots to perform complex tasks like assembly or delicate caregiving with greater accuracy. Another key theme is locomotion and navigation in complex environments. Research in this domain aims to equip robots with the ability to move through cluttered or unpredictable spaces. For instance, Wu and colleagues demonstrate how aerial drones utilize LiDAR for real-time obstacle avoidance in challenging settings like forests. Similarly, Zhou and team focus on collision detection for stable quadrupedal locomotion. The goal is safe navigation, critical for applications in drone operations, rescue missions, and industrial automation. Human-robot interaction and safety form a vital research theme, emphasizing trust and secure collaboration. Efforts are directed at enabling robots to understand human instructions clearly, with natural language processing resolving task ambiguities, as shown by Cesari and colleagues. Safety is also prioritized through whole-body control and collision avoidance techniques, as explored by Cabral Muchacho and team. The impact lies in fostering seamless communication and fail-safe mechanisms, essential for robots in collaborative settings like homes or workplaces. Turning to technical methodologies, reinforcement learning stands out as a core concept in robotics. This approach allows robots to learn through trial and error, often combined with imitation learning to replicate human actions. It's widely applied in manipulation and locomotion for dynamic adaptation, exemplified by a badminton-playing robot in a study by Wang and colleagues. However, challenges persist, including high computational costs and difficulties in handling real-world unpredictability, highlighting areas for further refinement. Several key findings from these papers underscore the rapid progress in robotics. A study on bimanual manipulation by Yang and team reports a 27.5% performance gain in real-world tasks. Wang and colleagues achieved a 94.5% success rate with a badminton robot against machines. LiDAR-based drone navigation by Wu and team outperformed existing methods in obstacle avoidance. In construction, Bikandi and colleagues reduced localization errors by over 50% using augmented reality. Finally, Chi and team introduced an open-source humanoid robot costing under $5,000, broadening access to research. Delving into methodologies, several common approaches underpin these robotics innovations. Reinforcement learning adapts to dynamic tasks but is computationally intensive. Simultaneous localization and mapping, or SLAM, helps robots map unknown spaces while tracking position. Dynamic movement primitives encode complex motions, though they require precision adjustments. LiDAR and camera systems provide detailed perception but face processing limitations. Optimization techniques ensure safety and alignment, often needing extensive prior data. These tools form the backbone of modern robotics advancements. Among the standout works is a seminal paper by Yang and colleagues on bimanual manipulation. The objective was to enhance precision in dual-arm robot coordination. Their method, the key pose and point flow interface, tracks gripper poses and object movements simultaneously. Results showed a 16.1% boost in simulation performance and a 27.5% gain in real-world tasks. This framework sets a new standard for industrial and caregiving applications. Selected for its breakthrough in spatial awareness and motion planning. Another groundbreaking paper by Wang and colleagues focuses on a badminton-playing robot. The goal was to develop a system for dynamic sports, combining physics-based locomotion with learning-driven manipulation. The robot achieved a 94.5% success rate against a serving machine and 90.7% against human players. Its significance extends beyond sports to any agile mobile task, making it a notable selection for its innovative hybrid control approach and real-world impact. A third seminal paper by Chi and colleagues introduces Berkeley Humanoid Lite, an open-source, customizable humanoid robot. The objective was to create an affordable platform costing under $5,000 using 3D printed parts. Findings highlight its robustness and modularity, with successful simulation to real transfer. This work lowers barriers to entry, fostering global innovation, and was selected for its potential to redefine access and encourage community collaboration in robotics research. Another critical methodology in robotics is simultaneous localization and mapping, or SLAM, used for navigation. This technique enables robots to build maps of unknown environments while tracking their position, vital for applications like drone safety in forests, as demonstrated by Wu and colleagues. It's also applied in construction monitoring for precision. However, challenges like drift errors over time in unmapped areas remain, underscoring the need for ongoing improvements in this area. Looking ahead, the future of robotics holds exciting possibilities. Deeper integration of artificial intelligence could enable robots to learn on the fly with minimal data. Advances in material science might yield safer, lighter components for soft robotics. Collaborative systems are expected to evolve with improved human-robot language interfaces. The trend towards open-source platforms will likely continue, broadening research access. Additionally, bridging the simulation-to-real gap remains a key focus for effective deployment. In conclusion, robotics stands at a pivotal moment. Recent papers demonstrate robots excelling in complex tasks, from sports to assembly, as seen in work by Yang and colleagues. Accessibility is expanding with affordable platforms like Berkeley Humanoid Lite by Chi and team. The future depends on enhancing safety, adaptability, and collaborative innovation. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from ArXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks